Hey y'all, we're going to look at another problem dealing with conservation of energy. You can go ahead and have a read through. Please pause it if you need to, because I'm going to just jump right into it. The first thing I notice here is that I don't have a picture. I don't know, ever since like pre-kindergarten, I'm like, I can't read that. I need a picture. So I'm going to go ahead and draw a picture as I read this little by little to try to figure out what really is going on here. So bowling alley, ball feeder mechanism is exerting a constant force. It's pushing the bowling ball up a ramp a meter long. Okay, so I got that. I got a ramp like this. The ball is going to go up the ramp. It's getting pushed somehow. And I do have that the length is 1 meter. All right, so I got a ramp, ball going up the ramp. Okay, that's the first part. I'm good. I'm good so far. All right, the ramp has an angle of 30 degrees to the horizontal. So that's this guy right here. 30 degrees to the horizontal. I assume that'll be important eventually. How much force must be exerted on a 5.0 kilogram ball? Sorry, I should say ball there. To get it to the top of the ramp, assuming that it starts at rest. All right, so that's going to be our goal. We need to get the ball from here to there. You may say, well, yeah, that's flat. Can I use some kinematics there? Kinematics would be nice, but I don't have a lot of information, right? Really, I know that it's starting at rest. I know that it's going up the ramp. There's a force being exerted, and it really just has to get to the top of the ramp, which means it's really going to end at rest. So maybe a little bit of acceleration here, maybe a little slowing down there. I don't know, but it seems like acceleration maybe isn't quite constant the whole time, right? It may be a constant speed as it's going up the ramp, but that seems overly complicated to me. So kinematics is probably not the right way to go. Next, we can think about forces. Yeah, force is definitely going to be important here. I could draw a free body diagram if I wanted, but I do need to somehow think about the fact that it needs to go from down here to up there, and how is the force going to accomplish that? Okay, so what really comes to mind as I think about this object that's changing height is change in gravitational potential energy, right? The ball starts at rest, which means no kinetic energy. It's got to get up to the top of the ramp, and it just says it needs to get there, which means it can end with zero kinetic energy. That's fine. But it's definitely getting gains in gravitational potential energy along the way. And so I feel like just thinking about that idea kind of leads me to the idea that probably gravitational potential energy is the way that I want to go. Now, that then brings up the question of, well, if I'm looking at energy, how does force come into it? Well, if you look at your equations, you think about the physics that you have, you may recognize that there is a connection between force and energy, right? Remember that work is equal to the change in energy, which is equal to force times distance, right? And so if we use this, this will make the connection between, as I was talking about before, the change in the gravitational potential energy and the force, which is exactly what we want. So our first step here then is let's find out the change in the gravitational potential energy. So if I define this as my 0 point, then I need to find out when I get to the end, what is my height? Now, I actually already have the information that I need, right? I know that this is 1 meter. The hypotenuse of this lovely triangle right here is 1 meter. I know that I got a 30-degree angle, and so you should be able to use trig, pull out your calculator, or use your math knowledge to figure out your right triangle, right? This is a 30, 60, 90 triangle. Yeah, that geometry is going to come useful someday. Maybe today's the day if you don't have a calculator. I guess if you have a calculator, then geometry is pointless. Just kidding, geometry teachers. Geometry's lovely. It teaches a lot of logic and other things, which is very helpful in situations like this. So we take that right triangle, we use our trig, and we find out that the height is 0.5 meters. All right? Now that we've got the height, we can calculate the change in energy. We are saying that it starts with 0 kinetic energy and ends with 0 kinetic energy for it to we just need to know exactly how much energy does it take to get it to the top. It doesn't have to have any speed at the top, it just needs to get there. All right, so what we're going to do is we're going to go ahead and say, well, no kinetic energy at the beginning, no kinetic energy at the end, no gravitational potential energy at the beginning because it starts at 0, but I definitely have some gravitational potential energy at the end. No elastic potential energy because there's no springs or stretchy things. We are going to have to assume that there's no friction here. We're going to be finding the net force, I guess. It would be nice if the problem had said no friction. It doesn't, but we're going to go ahead and do that here because this is my question. I can do whatever I want with it. So assuming no friction, then the only forces are the mechanism pushing the ball up, the normal force of the ramp, which is perpendicular, it doesn't do work, and the force of gravity, which if I look at the ball-earth system, gravity is then internal. It's what we consider a conservative force. So the change in energy will just be the gravitational energy final minus the gravitational potential energy initial. That will equal the force times the distance over which the force is being exerted. Now, we actually know that. That was given to me in the question. It's 1 meter. So, UGF is, remember, gravitational potential energy is mgh. So we'll go the mass, which was given to me, it's 5 kilograms, times g, which is 9.8, times the height, which we said was 0.5, minus the initial gravitational potential energy, which was 0, because the height was 0. So minus 0, it's just going to stay that way, equals the force times the distance, which we said was 1 meter. So now at this point, all we have to do is multiply 5 times 9.8 times 0.5, because the distance is 1, and we get our answer. So you pull out your calculator, you go beep, 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 and you get 24.5. All right, so 24.5 newtons equals the force. Now, I suppose I should go back and look at my significant figures. I had 2 significant figures there, 2 significant figures there. I do have a decimal there, so that's 2 significant figures there. So my final answer really should just be 25 newtons is equal to the force. All right, and there you go. We got everything that we need.